suspended silently 250 miles above Earth, a testament to human ingenuity glides across the cosmos. It is the International Space Station, a colossal structure visible from our planet, not merely a laboratory, but the most expensive and complex creation ever built by humanity. With a price tag exceeding $150 billion, its construction represents a saga of unprecedented engineering challenges, meticulously overcome in the unforgiving vacuum of space. This isn't just a space station, it's an orbital metropolis, forged by a global alliance against the very laws of nature. The dream of a permanent human presence in Earth orbit began decades before the first module of the ISS was launched. It was a vision born from the Cold War space race, evolving into an unparalleled international collaboration. This vision wasn't just about launching rockets, it was about designing a living, breathing laboratory that could endure the harsh cosmic environment for decades. From conceptual drawings to detailed blueprints, engineers across the globe grappled with how to design components that could withstand launch stresses, operate flawlessly in zero gravity, and integrate seamlessly hundreds of kilometers away. Building in space presents a fundamentally different set of problems than any terrestrial construction. On Earth, gravity is a constant aid, holding structures in place, guiding tools. In orbit, the absence of gravity turns every task into a delicate ballet. Tools drift away, massive components require precise robotic manipulation, and astronauts must contend with disorientation and the sheer physical toll of extravehicular activity. Every bolt, every cable, every module had to be designed not only to function, but to be assembled with zero-G physics in mind, or a simple push can send you spiraling. The colossal structure of the ISS didn't appear overnight, it was meticulously assembled, piece by intricate piece, over more than 30 years. This modular approach was the only viable method for constructing something so vast in space. The first critical step occurred in 1998 with the launch of Zarya, the Russian-built functional cargo block. Soon after, NASA's Unity module followed, precisely docking with Zarya. These initial connections were more than just hardware, they were the proof of concept for the entire assembly process, laying the foundation for all future expansions and setting the stage for decades of orbital construction. As the station grew, the need for a robust backbone became paramount. This came in the form of the integrated truss structure, a gargantuan framework providing structural support, attachment points for solar arrays, and pathways for power and data. Assembling these massive truss segments, each weighing tons and measuring tens of meters, represented an extraordinary feat. Astronauts, during numerous spacewalks, manually bolted and wired these sections together, often working in complete darkness or blinding sunlight, pushing the limits of human endurance and precision in an environment utterly hostile to life. Human hands alone could not build the ISS. The sheer scale and complexity demanded the integration of advanced robotics. The Canadian-built Canadarm2, a 17.6-meter-long robotic arm, became the primary tool for heavy lifting and precision placement. Capable of handling objects larger than a bus, it performed tasks too dangerous or complex for astronauts. Its dexterity and strength allowed for the delicate maneuvering of multi-ton modules, precise berthing operations, and even the inspection of the station's exterior. This robotic marvel was a cornerstone of the modular assembly process, an indispensable partner to human spacewalkers. Constructing the ISS wasn't just about assembly, it was also a monumental logistical challenge. Over its 3-decade lifespan, thousands of tons of equipment, spare parts, and provisions have been launched into orbit. Each launch vehicle, from the Space Shuttle to Russian Soyuz, Progress, European ATV, Japanese HTV, and commercial SpaceX Dragon, represented a critical link in the supply chain, delivering the next piece of the puzzle or vital supplies. Synchronizing these launches across multiple nations, ensuring precise delivery windows, and managing the vast inventory of parts, required unprecedented levels of international cooperation and mission planning. A significant portion of the ISS's staggering $150 billion cost is attributed to the sheer expense of launching components into space. Every kilogram of material lifted into orbit requires an enormous amount of fuel and specialized rocket technology. Estimates suggest that launching just a single pound of payload can cost tens of thousands of dollars. With hundreds of tons of modules, equipment, and resupply missions over decades, these launch costs accumulated rapidly, making orbital transportation the single largest line item in the ISS's budget. It's an astronomical fee for an astronomical address. Beyond launch costs, the development and manufacturing of ISS components themselves demanded extraordinary investment. Every piece of hardware, from life support systems to structural elements, required cutting-edge research and development. Materials had to be radiation-hardened, capable of withstanding extreme temperature fluctuations from -150 degrees Celsius to +120 degrees Celsius, and lightweight yet incredibly strong. Precision engineering, rigorous testing, and the production of one-of-a-kind components contributed heavily to the overall expenditure. This wasn't off-the-shelf technology, it was pioneering innovation, custom-made for the vacuum of space. The $150 billion cost isn't solely construction, it encompasses the immense operational and maintenance expenses over its long lifespan. Maintaining a complex, inhabited structure in space requires constant vigilance. Mission control centers operate 24/7, monitoring every system. Astronaut training is intensive and ongoing. Regular resupply missions are essential for food, water, and scientific equipment. Furthermore, the station requires continuous repairs and upgrades, often performed during challenging spacewalks. These recurring costs, year after year, represent a significant portion of the total investment, ensuring the station remains a viable outpost. One of the most critical engineering challenges was thermal management. In orbit, the ISS experiences rapid, dramatic temperature swings. When exposed to direct sunlight, its external surfaces can reach over 120 degrees Celsius. Minutes later, when in Earth's shadow, temperatures plummet to below -150 degrees Celsius. To protect the sensitive equipment and internal living spaces, the station employs an elaborate thermal control system. This involves a network of ammonia-filled radiators and fluid loops that constantly circulate, dissipating excess heat and warming components as needed, a complex dance to maintain a stable environment. Sustaining human life in the vacuum of space for extended periods necessitated groundbreaking innovations in life support. Early missions relied heavily on resupply, but for a permanent outpost, recycling became essential. The ISS is equipped with advanced systems that purify and reclaim water from astronaut sweat, breath, and even urine, achieving an impressive 93% recovery rate. Air regeneration systems remove carbon dioxide and replenish oxygen, creating a breathable atmosphere from what would otherwise be toxic. These closed-loop systems are vital, minimizing dependence on Earth and making long-duration spaceflight possible. The ISS is a sprawling city in miniature, requiring enormous amounts of power for its scientific experiments, life support, and communications. This energy is harvested by 8 massive solar arrays, spanning an area equivalent to several basketball courts. These arrays track the sun, converting sunlight into electricity. This power is then stored in sophisticated batteries and distributed through miles of wiring. Designing a power grid that could operate reliably in a vacuum, manage fluctuating loads, and seamlessly integrate new modules was another formidable engineering hurdle, ensuring the station never runs dark. Beyond the engineering marvel, the ISS's true purpose lies in its capacity as a unique orbital laboratory. The microgravity environment allows scientists to conduct experiments impossible on Earth, ranging from fluid physics and materials science to human physiology and advanced biology. Its external platforms provide unparalleled views for Earth observation and cosmic ray detection. This scientific output, enabled by the station's very existence, justifies a significant portion of its immense cost, pushing the boundaries of human knowledge and offering solutions to terrestrial challenges, a powerful testament to the value of this orbital outpost. Living and working aboard the ISS is a continuous exercise in human adaptation to an alien environment. Astronauts contend with bone density loss, muscle atrophy, and fluid shifts, requiring rigorous exercise regimens. They learn to move, eat, and sleep without gravity, constantly adapting their routines. The psychological challenges of confinement and isolation are also profound, mitigated by breathtaking views of Earth and close-knit crew dynamics. The station is not just a machine, it's a home, a microcosm of humanity thriving in an utterly hostile realm, pushing the limits of our physical and mental resilience. The incredible investment in the ISS has yielded dividends far beyond its orbital mission. The technological innovations developed for the station have found practical applications on Earth, improving our daily lives. Advanced water purification systems are used in disaster relief. Specialized materials and robotics contribute to medical devices and industrial processes. Even the software and control systems developed for station operations have influenced terrestrial engineering. The $150 billion wasn't just spent on space, it spurred advancements that continue to benefit humanity, a tangible return on an astronomical investment. As the ISS approaches the end of its operational life, its legacy is undeniable. It stands as the zenith of international cooperation in space, a symbol of what humanity can achieve when working together towards a common goal. It has provided an unparalleled platform for scientific discovery and invaluable experience in long-duration spaceflight. The lessons learned from its engineering, assembly, and operation are directly informing future endeavors, including missions to the Moon and Mars. The ISS is not just a destination, it is a vital stepping stone, preparing us for humanity's next giant leap into the cosmos. From the first humble module docked in 1998 to its current sprawling configuration, the International Space Station is a monument to human ingenuity and perseverance. Its $150 billion construction, undertaken against the most challenging backdrop imaginable, showcases our capacity to dream big and build bigger. The unprecedented engineering hurdles, the painstaking modular assembly, the continuous innovation in life support and robotics, all converged to create this orbital wonder. It is a powerful reminder that with vision, collaboration, and unwavering dedication, humanity can indeed conquer the impossible, constructing not just a station, but a legacy among the stars.